Okay, let's start. Thank you for the introduction, and thanks for coming so early. Very happy to be here, and very happy that we have a machine learning school in applications of science. I think that's great. So today I wanted to talk about, let's say, an opinionated way of thinking about neural networks that I hope you will use it as one of your, let's say, tools in your toolbox. I don't expect you to agree with everything I say, but I hope some of this will be nevertheless useful. So the title of the talk is Nothing Makes Sense in Deep Learning Except in the Light of Simplicity Bias, which you might recognize as a play on famous quote that nothing makes sense in biology except in the light of evolution. So first of all, what is simplicity? So there's this, I don't know, analogy or joke about how physicists approach problems. So if you were to ask a physicist to calculate for you a milk yield of a farm, he would start with something like, let's assume a cow is a sphere that produces uniformly milk and is suspended in vacuum, right, or in Kraków. So that's how we'll think about simplicity. So we'll say that something is simple if it has removed irrelevant details for a given task. So I hope it makes sense, and we'll try to make it more precise as we go. So in the first part of this talk, I wanted to, well, first of all, introduce so-called simplicity bias in deep learning, and also talk about its good implications. You might foresee that there will be also bad implications later, but let's first focus on the good. So let me take you to 2017, so somewhat early days of deep learning. And in 2017, researchers were worried. So they're worried by the fact that deep neural networks were pretty large compared to the size of the data set. The prevailing wisdom, if you will, was that you shouldn't really train a model that has more parameters than data. And researchers in deep learning definitely didn't care about this prevailing wisdom. So this plot works like this, that on x-axis we have a number of operations of the network, or size of the network is the size of the blob. And on y-axis we have performance. I think it's on ImageNet. And you can see how larger models are getting better. And in particular, at some point, these models become larger than the number of data points in the corresponding data set. As a kind of related story, there's the story of von Neumann criticizing his fellow physicist when he introduced a theory that had 5 parameters, and he said something like that if you give me 4 parameters, I can fit an elephant, and if you give me a 5th parameter, I can make him wiggle his trunk. And this is a figure from a paper that did try to achieve that, and that's a plot of this function. So in 2018, we, as a form of response, try to tackle the simplicity bias. Actually, let me start from an earlier paper, also from 2017, and then go to ours. So against this backdrop, still in 2017, a group of researchers in a now pretty famous paper, Understanding Deep Learning Requires Rethinking Generalization, propose a thought experiment, or a simple experiment that suggests that neural networks might be actually only memorizing your data set. So the experiment works like this. You take your data set, but you randomize the labels. So for example, your dog will become a cat in terms of the label. Another image of a dog might become a bird, etc. So the main result in the paper really is that if you train neural networks on this type of data and other variants, so each color is a different type of how you would, remove information about the label input association from your data set, the neural network is actually still very happy to fit your data. So here we have on x-axis training step, on y-axis we have performance, and you can see that in all cases, and in particular red, which is random labels, your loss goes down. So are these models actually learning something on true data if they can just as well fit random data? So as a response, in 2018, we proposed that deep neural networks exhibit a form of simplicity bias, which we, let's say, phrased as deep neural networks first learn simple patterns and then only start to memorize. And to illustrate this, we came up with this simple experiment. It's actually a plot from a reproduction from a different paper, because unfortunately our paper doesn't have very nice plots. So the experiment goes like this. You add to your data set a percentage of examples with randomized label, but you keep a portion of your data set as clean, so unchanged. So blue will be unchanged, orange will be mislabeled, and test this clean data set. And then let's train the neural network for 40 epochs. And something very interesting happens. So you feed your clean data, but you actually reduce your accuracy on the orange data, so on the mislabeled data, and only then start fitting it. So there is this interesting period of your learning where your neural network kind of knows which are the noisy examples, kind of says, no, I'm not interested in understanding them. So that's a very interesting point. After that, you can see that we feed happily the mislabeled data, and test accuracy also goes down. But there is this period here where neural network can still train, even though it has noisy labels. And this has big implications for applications in science, because in science, unfortunately, we always have pretty large amounts of noise in our data. It's very hard to really have like super clean data in science applications. Also, you might think it might actually serve as a form of denoising of your data set, because if we know that here we do not fit noisy data, then we can actually just remove all the data that is not learned until some epoch, and we'll talk about that as well, please.
Oh, it works now. So what exactly happens at this point? Because I see that the trajectory of the accuracy on unchanged data changes as well. So I think it's not random that at this point something weird happens in the training process. So it's like a learning rate, or?
Yeah, first of all, please ask questions during the talk. This talk is kind of modular, so we can just cut something at the end. I would much rather discuss specifics. About this, I'm actually not sure I understand the question. So, okay, let me rephrase what's the experiment, and you can let me know what is confusing. So you just mix in your data set, like 80% of clean data, 20% of mislabeled data, and you just train on the whole bunch. And then you track accuracy on the subsets. So if you track accuracy on the subset, the mislabeled subset is actually unlearned in a way in the early epochs of training.
Yes, but I see that at this point there is also a peak in the accuracy of the unchanged data. So I was wondering why.
Oh, right, of course. Yeah, so in this experiment there is learning rate schedule as well. That is changing by increments of 10x. Yes, please.
Yeah. So basically, what you're showing is that if you have the more mislabeled data you have, the more likely the model at some point is to just memorize also the clean data. That, if that makes sense.
Sorry, could you rephrase that?
So if you train a model,
yeah,
and you have a lot of like noisy labels,
yes,
right?
Yes.
Because of the noisy label, the model is more likely to choose the path of just memorizing, well, compared to if there were no mislabeled data. Or is that wrong?
Well, what I wanted to say, though maybe this data speaks another story as well, is that if you mix mislabeled data in your data set, your model actually picks the clean data as a path. Like it picks learning on clean data first, and then memorizes. So it's kind of the phrases deep networks learn first simple patterns, and then memorize. But once you are past this phase, you actually reduce your test accuracy and you memorize. So there's like a trade-off, right?
So you think the learning curve of the clean data would look similar if the mislabeled data wasn't there? Do you think the fact that there is mislabeled data in this training changes the path of the blue line?
No, it doesn't. I mean, it does in some sense, but not in the sense of what we are trying to say here. Yeah. Thank you for the question. And yes, this is great. Any other questions are very welcomed. Yes, please.
So I want to know that in this case, we have this assumption that our mislabeled data shouldn't have any correlations.
That's a great question. Right, so this happens also if you have some sort of correlations, but indeed here there are no correlations. So what I mean specifically is if you were to repeat this experiment, but instead, as mislabeled data peak, like a subset of your data that you just know is more noisy, but is coming from real distribution, so it has some correlation with the input, you will still see some versions of this, of this phenomenon.
Yeah, I also have one. What would happen if the portion of mislabeled data was larger than the portion of unchanged data?
Right, right. So the more noisy data you have, the bigger price you pay in terms of generalization. So it does hurt. And we'll actually talk maybe about theory. The actual problem becomes when the gradients of the noisy data start to overcome the gradients of the clean data. It's less about the percentage, but more about the gradient norms. But yes, of course, we want to have as little noise as possible. There is no free lunch, here.
Thanks.
Cool. Thanks a lot for the questions, and please ask any questions. This talk is kind of very modular. Right. So you might wonder also, what do these simple examples look like? And the whole premise of the talk is, on whatever data you train and whatever model you train, you should always think about what examples you first learn, because everything else will be kind of bootstrapped from that. So if you train a CFAR, a convolutional neural network on CFAR10, which is a simple data set of images in 10 classes, the simple examples of airplanes, so examples that are learned first, will be all on blue background. And this is contrasted with hard examples, so learned later consistently, which all are on diverse backgrounds. So initially, a convnet will have a very strong bias to recognize airplanes just by the color of the background. And it has implications for robustness and stuff like that. So you might notice that if there is this quote-unquote magic capability of neural networks to learn first on clean data and then on noisy, we might use it to our advantage. And here's a very interesting paper, robust and on-the-fly denoising of image classification, where the idea is very simple. You just train a bit, and then once you train a bit, you remove examples that have large loss. So, for example, you can plot after training for a few epochs loss of clean data here, and of noisy data it's here. It's a histogram, and pick a kind of a threshold above which you just remove data. So you train, effectively on less data. And it's also something we have explored at molecule.one, where we work with noisy data coming from an automated laboratory. It also helps there. I think it's a pretty interesting tool to have in your toolbox. And there's like a lot of papers that do this. I have singled out one of them. In terms of results, in general, how these papers, let's say, compare? Yes, please.
Isn't this kind of cut risky for the reason we've just explained in the previous slide? So maybe it's not noisy data, it's just more complex data for
yeah, that's a very good question. So first of all, it's a hyperparameter, so risky, yes, it's a hyperparameter that would be good to be tuned. The premise is that there is a threshold where it pays off. I mean, that's the whole kind of story of the paper. Also, actually, even if you cut complex examples, it also sometimes helps with your generalization if you care about very broad generalization. So it's also not a clear cut that you shouldn't exclude very complex examples, even if they are correctly labeled.
Thank you.
Thanks for the question.
What if you have class imbalance and there's certain classes you have very few examples of? Wouldn't you cut the rare classes?
Good question. Yes, I guess this has all sorts of weird biases. So indeed, maybe it should be a balanced data set. Okay, thanks. So in terms of comparison, and maybe we'll come back to that in the context of another paper, people compare doing nothing to the method. In this context, it's called ODD. Excuse me, and compare accuracy after training on a noisy data set. So they try either clean data, 20% noise examples, 40% noise examples, or mislabeled examples. and also CIFAR 100. And interestingly, if you compare the numbers, using this method can give you like a very large boost in performance in this difficult setting in which you have almost half of your data mislabeled. You get around plus 20% when you use this method. I wanted to also talk about how this relates to language models. I think it's quite interesting. So for that, let me talk about this concept of emergence. In general, I would argue everything that has happened with language models hasn't been predicted before. It's more of an emergent property. So we train models to predict the next word. I mean, at least in the first phase of training models such as ChatGPT. And then you get all sorts of properties. This maybe has been first noticed. I mean, it's an oversimplification, but one of the early demonstrations of this emergence is in the paper Unsupervised Sentiment Neuron by Chris Olah and others. And what they show is that when you train a language model and then you kind of run it on reviews of I think, movies or something, it turns out that there is like a single neuron in the network, and I mean literally a single neuron, that gets very activated and excited when the whole network is reading positive reviews, and it's get very negative when, like literally negative, when the reviews are negative. And here's value of the sentiment neuron. Here's number of reviews, and you can see that there is like a clear separation in its activations. And there's nothing really clear in the, let's say, pre-training, like training on the prediction of the next word that would, you could predict that you would get sentiment neuron. That's an emergent property. So I will argue that this is also related to, I mean, not this specifically, but this type of phenomena are also related to the simplicity bias. Another emergent property, arguably much more important, is the ability of in-context learning. It also has emerged from predicting the next word in a somewhat weird fashion or unpredictable fashion. So normally, sorry, this font is small, but basically it's, I even have to read it here. So it's basically about model, let's say you're fine-tuning a model to do translation for you from English to French. So normally you would change parameters to achieve that, right? You would change your model parameters to be better at translation. In context learning, and in particular in zero-shot learning, you describe your task. I guess you're all familiar with this. So you just ask, translate English to French. How does this capability emerge from, language modeling? There is this very interesting series of work on induction heads, again by Chris Olah and others, that I highly recommend. I will briefly mention this and how it relates to simplicity bias. So I won't go into, let's say, the details of how it works, but induction head is a circuit, so a subset of your transformer that is formed of two attention layers that allow the transformer to predict, let's say, B from A in a sequence of tokens where you have like A, B, and then you read A, and you have to predict B. And the thesis of people researching this is that these circuits or subsets of transformer are ubiquitous in transformers, meaning that if you train these models in transformer language models, if you train these models on language modeling, almost invariably there will be a subset of neurons doing precisely that. So again, I won't be talking about how this is implemented, but I will show you kind of what I mean on an example. So let's say you're reading the first page of Harry Potter. And the way this visualization works is that blue is the token you're reading, and red is kind of the attention strength over tokens if you do some sort of attribution of attention back to the input tokens. So for example, if you're predicting full stop, you do not attend to anything really. But then, yeah, that's what I said. But then interestingly, if you predict, well, you are predicting Earth here, right? This token from D, this is what you read. The model attends actually to the instance of the same token in the previous text. So there is a form of induction, right? Because it tries to look for, when there was D before, it doesn't show up in attention strength, but this is how it works. And then kind of reads what's the next token, and it's Earth. And it does the same when it is predicting Mr. Dursley. So to predict Earth from Lee, model attends to the previous Lee. And more particular, it tries to look up the copy of the token it is reading and looks up what is the next token. So that's what induction head does. Again, I'm really not describing the mechanics of how it's achieved. But then how does it connect to simplicity bias and how does it connect to in-context learning? So the authors run a very interesting experiment, and this is both on simple transformers as well as on pretty large models. They measure in-context learning score. To measure if your model is able to do in-context learning, what you can do is you can measure the loss you have on first token and then on some token later. So just see how better you are at predicting the next token as you read the sentence, right? That's in-context learning. So they measure 500th token to achieve that. So this is a bit small, but on x-axis you have the training time, and on y-axis you have in-context learning score, and this is for a one-layer model. So if you remember, I mentioned that you need 2 layers to do that. Basically, the first layer is doing the copying of the previous token to the next token, and then the second layer is actually doing the induction. So if you just train a single layer transformer, that's a weird model, this loss really goes down slowly. But then if you add just 1 layer more, this is on a toy task, but again, this type of phenomena is visible also on larger models. You get very early on in training very rapid drop in the in-context learning score. So just like with the airplanes, something, let's say, magic or important happens in the early phase of training, where all of a sudden you get much better at in-context learning. And the way Chris Ola put that is transformers desperately want to do meta-learning. And I think it's pretty accurate and illustrates this simplicity bias of transformers. So what I wanted to mention in this first part is that simplicity bias is a fundamental phenomenon that is key for understanding any deep learning system. Mostly I talked about this form of simplicity bias that neural network first learns simple example and then only starts to memorize. And this has all sorts of, let's say, implications. For example, it will detect airplanes using the blue background, but also it leads the model to learn these induction heads that then are key part of the capability of model transformers and language models of performing in-context learning. I also mentioned an interesting, I think, tools of unsupervised removal of noisy examples using this phenomenon that I recommend you to try if you are working with noisy data sets. Yeah, so this is the good. There will be bad as well. Do you have any questions about this part?
So basically, everybody in deep learning, I guess, does adhere to this by using early stopping, right? Doing like early stopping, where like when the validation loss decreases, stopping training would kind of automatically solve like the learning curve you showed, right?
Right, that's a very good point. So like part of it, but yes. So if you do early stopping on a noisy data set, like you do not get like the same benefit as if you were not to train on this data. But yes, indeed, early stopping will help you thanks to these effects. So yes. I don't know if I understand your question correctly.
No, because in the plots you showed,
yeah, that was the point of early stopping.
The point where it got worse on
the
test set was also the point where it kind of overfit on the noisy data, right?
Yeah, that's definitely correct. So indeed, of course, use early stopping. That would be one thing, but yeah. I'm not sure if there's a question there, sorry.
No, I just wanted to get your like insight whether this early stopping does solve this or whether you would need extra techniques in practice.
Well, notice that there is no really problem here that we are solving.
But data,
I mean, there will be, but not yet. But yes, if you have noisy data, you should use early stopping. And maybe to add context to that, if you just use early stopping, but you do not denoise your data set, specifically talking about the, let's say, effect of noisy examples on your generalization, you won't get the same performance. So like, it's not free lunch in the sense that you can just do early stopping and you're fine. Yep.
Can I have just a follow-up question? Do I understand correctly that the noising data means that the removed part was never seen by the neural network?
Yes, that's what I refer to, yes.
Okay, so what is the point of including this data at the very beginning?
Right. Well, sometimes you don't know which data it is, right? So, for example, you have a big data set of chemical reactions, which is kind of what I deal with, and it's hard to know which ones are quote-unquote noisy. You do not have really the resources to ask chemists about everyone, and also chemists won't know, as an example.
So technically this data should be removed before one epoch ends?
In an ideal case, you would pick the subset of your data that is the most appropriate for your task. Maybe to clarify, the use of the removal technique that I mentioned is when you don't know which ones are noisy. So what you do is you first identify them and then retrain on clean data.
Okay, thanks.
Thanks. Yeah.
So first, just to clarify, like if I understand correctly, about the connection of simplicity bias and induction heads. So do you mean that kind of this using induction is this simple thing that is discovered, and this is kind of this?
Right, that's what I meant. Yes, yes.
Okay.
Sorry if that was
yeah. So yeah, and then like another question. So do you need to have like a diverse data set, or like some threshold, or like of like complication of that data set to these induction heads to actually arise?
Right.
Or does it also like these are formed also for like simple data?
Right. It seems to emerge from very simple data. I mean, according to the experiments from the paper I mentioned.
Thanks.
So I'm a little bit also going to follow up my previous question. So normally when we have in many of the data sets that we have, we assume that the noise is Gaussian, or we have white noise or something. So it could be some kind of correlation. So if you have a higher density of your noise, I think that then the learning process should be like divided two parts, like the real data from the noisy data, so you have two classes. But if you have more noise, then it will learn noise, as you said, first, and then maybe it doesn't learn what is the pattern of the real data there.
Sorry, I didn't understand your question.
So I said that if we are going back to your first graph, so if you have more noisy data, is it possible that our neural network first learn the noisy data?
Okay, sure. Yeah, I think it's related to a question also from previously. Yes, it is possible if your noisy data dominates your clean data. So basically, yes, it is possible. Though, fortunately, we train, for example, let's say language models on, web scale data, which is ridiculously noisy, and still, I think most of the complex patterns are not that negatively influencing training.
Hello, I wanted to ask you to step through the reasoning of that last bullet point again, please, because I'm not sure I'm actually following, like, which part does the simplicity bias exactly pertain to?
Sure. So simplicity bias pertains to the, let's say, let me try to rephrase that. So let's say there's something in the learning process that where you start from randomly initialized transformer, you end up after very little time with capability of doing induction. And this capability of doing induction is just one model from a huge model space. And it's very unclear why specifically this single model from the model hypothesis space is chosen.
So, okay. And basically in this case, the argument then is that this particular induction head, you define that as a simple, as a simple sort of mechanism, in otherwise unrestricted class of functions. So this is where the simplicity lies.
Yeah.
Okay. Thank you.
I have one more question about the transformers, actually, and the induction heads, because there is the, I think, one or even bunch of papers from the last couple of months that are showing that transformers are, in some sense, doing some kind of SGD optimization during go through. And do you think it could be this phenomenon that enables to, I don't know, if establish these induction heads or move them up or something like that?
Yeah, it is a fascinating phenomenon. I think one of these has trained transformer on a sequence of, let's say, regression task where it was like sequence of inputs, and then the label was it was basically a sequence of input-output. It was basically as if you were to train scikit-learn linear regression by feeding it to transformer, and the model has learned more or less optimal way to solve it. I mean, there is again something very interesting why it would, and I think a useful way to study it would be to see what sort of things happen in the transformer in early epochs. Because once you learn something in early epochs, you often later build upon this. You know, just like with, you know, childhood has huge importance on, you know, the whole life trajectory. It's kind of the childhood of the model. So I don't know if there is a link between this and induction heads, but maybe. Yeah. Thanks for the question.
How did you identify the simple examples for the airplanes with the blue background?
Right. So that's so this was introduced in our paper, and what we did, we trained multiple times neural network for like one epoch or something, and we looked at which examples are always learned early on, regardless of the shuffling of the data set and at the random initialization. So these examples are consistently learned the first epochs of training, regardless of how you present your data to the model.
Do you think they would also result in a larger activation norms in comparison to other examples?
Yeah, I'm not sure about that.
Okay, thanks.
So I think it may all come down to proportions, but I'm interested in if, in your opinion, if we have data sets with some amount of noisy data, is including noisy data beneficial because of increasing the data set diversity, even if we risk that it's noisy, so it's kind of inaccurate, or is it better to put some more effort into cleaning your data, even if we know that the amount of data will be lower?
Sure, I think you answered your question. So it's a question of proportion, right? Also, there was a question about this being risky of removing data. So it's really a hyperparameter. For example, at molecule.one, as one very specific example, we saw that if you care about out-of-distribution generalization, then removing noise more aggressively sometimes pays off, because if you have complex examples, you can be kind of, there is very little hope that very complex example will help you generalize a lot in terms of you learn something from them that doesn't apply only to in distribution. But that's a very, narrow answer, but as an example.
I wanted to ask one more question about this unsupervised removal of noisy examples.
Yes.
Did people sort of put some of your insights into use for stuff like curriculum learning or similar applications?
Yes, this is actually a very rich domain. Like using this effect of you learn first simple example, like there's hundreds of papers that, let's say, use it in different ways, and in particular, I guess, things related to curriculum learning.
Thank you.
Okay, so I have a question regarding the last point on the current slide. How do you know that induction heads are necessary for in-context learning?
Oh, right. It's a It's a long argument, basically. So I would actually refer to the paper I mentioned, because like you have all sorts of experiments. For simple toy tasks, you can try to do causal kind of experiments. Like if you have a toy task where you know what is induction doing and what is the optimal way of solving it, you can kind of try to remove this and show that it doesn't work, that the model doesn't work. Then you have all sorts of correlations that you can draw. So it's a very good question, and I think it's a bit of out of scope to go through all of these arguments. And actually, I don't remember them in detail. But it's a very nice blog post, so I would recommend.
Great, thank you.
Yeah.
Could we go back to the last graph you had?
This one?
Yeah. So on this one, just to double check the so what of the graph. So does that imply that in the first epochs of transformer training, it learns the general language model, and then switches to context-specific sequences? Like,
I don't think this data speaks this story.
So
but indeed, there is something like that, that in early phases of training, there is learning of syntax. So that's not this, let's say, simplicity bias of language models, but it's not this result.
So this drop in...
yeah, this is drop in in-context learning score, which is a custom metric introduced by the authors, where they basically measure how good the model is at predicting first token versus like 500th token in a sequence. So it's basically a proxy for meta-learning capability, if it makes sense.
Well, it looks like it's narrowing that with training. It knows for the specific fields, let's say, or specific tasks, which it was in context learned on, that it knows better the sequence like within the task. It's still, because the score goes down, it's still pretty uncertain, or relatively like bad on predicting the beginning of the what task it is. But then when it knows which through conditioning, when it knows which task it is, it actually can predict within.
Okay, in this sense, yeah, you can. I think that's a reasonable phrasing of that. Yeah. Thank you.
Thank you. Amazing questions. The last one, and we want to listen to.
I mean, we can also finish this talk here. It's perfectly fine. But
can you just explain very briefly what is the difference between induction and actually memorization? Because for me, that's the example you show is just you remember the previous word, and there is like nothing about the context really.
I mean, yes and no. So indeed, that's a form of memorization, but a very specific form that really helps you generalize. I think it's a bit confusing, but I don't know how to answer it differently. It is a memorization in the sense that you just copy, but then authors show, for example, evidence that this copying can be very smart. So for example, it can be copying where you actually copy kind of the, let's say, the relation that one word is in English and the other is in French or something like that. So it's kind of, it is kind of confusing, I agree. Yeah, I hope it answered. Yeah. Should we move on? Or okay, good. Okay, thank you for questions. I mean, the whole talk is really about simplicity bias, and we can finish here, but we can also try to go to another section. And thanks for all the questions. Like it's amazing that that you asked this, and thanks for that. Okay, so there was the good. You have also thought a bit about the bad, but let's talk about the bad more specifically. Let me start with a story. So there was a horse, and the horse was called Hans, and it was very famous at its times, and it was doing a trick where the showman was showing it, I think, 2 numbers on a blackboard, I think, and the horse would then tap the number that corresponds to the sum of the numbers, right? So it was an amazing trick because horse shouldn't be able to add. And later they found out, and I think it was by accident in the sense that the showman actually didn't know that, it was showing the horse very small cues when to stop tapping, right? Like it was maybe leaning a bit forward or something like that. So this story is meant to illustrate that sometimes you can solve a task in a simple way, but it's not what you should do, right? So this has been christened shortcut learning in some subset of community of deep learning, and it manifests itself in all sorts of places. from language models to medical applications. And again, I think it's really important to think when you're solving a task with deep networks, like what shortcuts can emerge in my training? Especially if you are trying then to deploy your model in some setting, then it's absolutely critical. And people don't think about this, I think, enough. One famous example is there was a model reading X-rays and predicting whether or not there's a specific disease, for example, pneumonia based on the X-ray. But some of these X-rays had hospital token somewhere in the top right corner. And there was some correlation between between which hospital the X-ray is coming from and how prevalent a given condition was. So the model was solving the task partially by looking at the hospital token. And there are all sorts of examples you can think about of this kind. So for example, if you train from scratch on a data set where you have a lot of sheep against grass, then to learn to recognize your sheep based on or not on the existence of grass. So that's this example. It's a nice survey that I recommend shortcut learning that talks about this in all sorts of ways. There is interesting, I think, version of that in language models. I probably don't have to convince you that there is a lot of shortcut learning in models like ChatGPT, but there's one that I liked a lot. So one type of shortcut that seems these models implement, and they seem to be better at this the larger they are, in a way, so worse, right, because they apply it more, is answering puzzles by copying answer to the puzzle from the training set, but it really fails if the puzzle changes a bit. So I ask here, it's from my interaction with ChatGPT, I guess they fixed it already. I think they are really fixing like case-by-case examples, but so I'm not sure if this will reproduce, but anyhow. What weighs more, a pound of feathers or 2 pounds of bricks? And it goes like this. Both a pound of feather and 2 pounds of bricks weigh the same amount, which is 1 pound, right? The trick in the question is that the weight of the feather is given in terms of a pound, while the weight of bricks is given as 2 pounds, right? So it's utter nonsense, right? There is a fascinating work, there was fascinating contest, and there is also a paper associated with it called inverse scaling price, where usually, maybe as you know, the larger the models like it is, the better they are in all sorts of tasks. That's called scaling laws. The authors of the prize, Ethan Perez and others, set out to answer whether there are tasks that have inverse scaling. So the larger your data, the worse your model. And they indeed found some, and the prize now is, and the contest now is finished. And some of these that they found are actually similar to this one. There is like a puzzle or something like that, a trick question, where the model actually has memorized some sort of way of answering it and doesn't really read the specifics of the question. And I don't know why this happens. Like maybe if you have larger models, it's more easy for the model to actually memorize all sorts of these weird puzzles, but it's hard to say why this happens. Maybe more interestingly or more importantly, recently there was a paper, Faith and Fate, Limits of Transformers on Compositionality. It is a bit too negative, but I think it illustrates and names one specific issue with these models that's related to shortcut learning. So they say, transformers solve compositional tasks by reducing multi-step compositional reasoning into linear path matching. Shortcut learning may yield fast correct answer, but does not allow for robust generalization to uncommon or complex examples. So there is this form of shortcut learning where you simplify your reasoning by copying subset of your reasoning, so to speak. I won't go into details of this, but I recommend this paper. I will just show one result from it. So the way they show that there is some form of, let's say, shortcut learning or memorization is that they test the model on a range of tasks that differ in terms of required complexity of reasoning. They call it graph depth, so they represent actually reasoning problems as forms of graphs. And they train only on, let's say, simpler problems in some sense of simplicity. And then they show that models, I mean, in this case, GPT-3, regardless of whether you're fine-tuning it, performing 5-shot in context learning or performing 0-shot learning, they always perform pretty poorly at these stages, which goes to show that they don't learn, let's say, pure algorithms, they learn some sort of like fuzzy reasoning. It's kind of obvious that this happens, I think, from, let's say, perspective of deep learning, but it's still a very useful thing to name this phenomenon and have a benchmark. So it's also a very interesting paper, a very interesting benchmark that's part of this paper. Yeah, so in this short section, I wanted to say that unfortunately, deep and biological nets learn first shortcuts. So sometimes simplicity bias works against you. And I talked about Hans, that was this famous horse that learned to count. And I also mentioned specific forms of shortcut learning that are there, right? So I mentioned hospital tokens being present on X-rays. I mentioned ChatGPT potentially copying puzzles without reading it. And also language models reasoning partly by some forms of shortcut, though I haven't really described specifically what these shortcuts are. I don't know. Do you have any questions?
So I wanted to ask about large language models and these examples of inverse scaling.
Yeah.
So I think in the GPT-4 technical report, they report that for at least some of these tasks, I don't know if this is majority or like just some examples, they kind of reverse this trend. So basically, the model, if you increase the size, then it first deteriorates, but then if you really go to this huge scale of GPT-4, then it like goes back and is like the best. So yeah, do you have some comments on this and like how this relates to this simplicity bias?
Sure. Well, thanks for adding this. I should have mentioned this. Indeed, that's the case. So first of all, I don't know if that's the strategy they are performing, so it's more of a hypothesis. Indeed, what you say kind of contradicts it partially, so maybe it's not true. Second of all, GPT-4 kind of actually does similar things. I played a bit with it. And also, it didn't, reverse the trend for all of them. So I agree that, and it's an interesting thing, interesting question. Like, are there tasks that, would be inversely scaled for any model, right? And we don't know that right now. Like I think that what you mentioned kind of says that these are just very difficult, but maybe scaling 10x what we have would solve them as well. So not really any, just additional thoughts about what you said.
But do you think it may be possible that like when you scale to like even larger and larger models, these are learning in some sense like even simpler and like more bias into this like generalizable solutions and like that this could be the reason they would solve this?
Right. I mean, you're asking me if scale is all you need. Like, I don't know, right? Like, I mean, people have all sorts of opinion. It would be nice because that seems simpler to solve intelligence, but I don't know. So, not sure.
So, when we ask those sort of problems to young kids, do you hear me?
Yes.
Usually, like they answer incorrectly.
Yeah, and then you. Yeah.
So I think this kind of bias is also present in human beings.
Yeah.
And so, like, my question is twofold. So first of all, do you think do you think this is true? And the second one is, do you think we can overcome this kind of problem and biasing? And if so, maybe we can achieve a level of intelligence which is even better than humans.
Yeah, thanks for this question. So yes, indeed, we teach humans by telling them how to think. And that's actually a very recent trend. So there is a paper, Let's Verify Step by Step by OpenAI. There is also a paper, Thought Cloning by Jeff Clune, and I actually referenced that one in my talk. And both of them show basically what you're saying, that that we can improve a lot generalization in this robust sense by supervising the model not on the outcome but on the process. So for example, in this case, in the, let's say, application of Let's Verify by Step paper would be that you give this part to human annotators and they say whether or not the reasoning is correct. And that's a very powerful tool, it seems. So yeah, maybe. Again, like, I don't know, but all of that, what I'm telling you here it's not about some insolvable problems, it's unsolvable problems. It's more of a way of thinking about deep nets. I'm not saying that requires, you know, like abandoning deep learning. I guess I would be the last person to say that, but yeah, it's more of a way of thinking.
And sorry, one last thing. So maybe via understanding this kind of bias in deep learning, we can even learn how to reason in a better way and actually improve our own intelligence based on the results of these kind of research. So I think it's very, very interesting. Like, I mean, we've evolved to basically solve pretty basic problems up until now, and maybe these more complex way of training humans as well may lead us to a next step in intelligence.
Yeah, thanks. That's definitely an interesting point, and yeah. Oh, and by the way, I really think using ChatGPT and stuff for education is great. So if you haven't tried it, I recommend it. It taught me quite a lot about chemistry. Yes.
I'm curious if this simplistic bias is related to this Occam razor, like this model selection argument. Like you prefer the simple explanation to the solution or something.
Yeah, I mean, it is related, of course. It's the same quote-unquote simplicity that both of these talk, and then let's say devil is in the details of defining it. And yeah, so basically the answer is yes. Like this is very similar. Yeah. Oh, thanks for.
So, in your opinion, because it is said that deep nets perform as well as they do, sometimes even better than humans, because sometimes they find correlations in the data that humans are not aware of.
Right.
So it's like that behavior and finding those shortcuts kind of two sides of the same coin, in your opinion?
Yes, I would say so. Yeah, so it's kind of sometimes that's good, sometimes that's bad. Like that's the premise. Yeah.
Okay, we are ready to go.
Okay, thanks for questions. So the third part is pretty straightforward. I wanted just to mention a bit how to combat it, and it's what you would predict. Either you can directly attack the problem, or you can train on a larger data set. But I wanted to highlight specific papers in these two camps. So one insight you can use is that if simplicity bias causes the network to learn shortcuts, then that's great, because you can train a network that identifies shortcuts and then use it to train another network that doesn't use shortcuts. It's pretty straightforward. There is a bunch of papers that use now this idea. One of them is learning from failure. Another is fighting fire with fire. I recommend checking them out. So in I think fighting fire with fire. No, that's actually learning from failure paper. Sorry for that. They train two models, and they train them concurrently. So you have on the top the biased model, and you have on the bottom biased model or amplified biased model. So you train the bottom network using a modified cross entropy that basically emphasizes the loss of simple examples. So if it's kind of applying a transformation to your cross entropy such that you learn even more quickly simple examples. And they achieve it by picking a loss such that the gradient of the loss is the same as gradient of the cross entropy times probability of the predicted class to the power of q. But that's an irrelevant detail. Basically, it is amplifying simple examples. And then concurrently, as I said, you train the second model that has weighting on each example. So now you don't train on average loss, but you train on weighted average, right? And the weights are basically such that if the biased model predicts the example to be simple, then you actually want to have a lower loss on it, right? So here you have cross entropy of the bias model divided by some normalization, right? So it's cross entropy of bias model plus cross entropy of the biased model. And that's all. It's pretty simple to implement. It's also useful, I think, to talk a bit about how people evaluate these type of methods. This is like a whole sub-community, and they have actually quite interesting data sets that I think sometimes of them as kind of paradoxes or puzzles in deep learning. So one of them is colored MNIST. In colored MNIST, you have some percentage of images that have digits that have aligned color of the digit with the digit. So for example, all 5s are green, or 3s are yellow, or 0s are red. But then you test on clean data set where you don't have this correlation anymore. So you can see how this is a bit of a paradox. So should you use this shortcut or not, right? Like it's kind of a mind twist, you could say. Then there is corrupted CIFAR10, which is very similar, but now you take CIFAR10 images. So we did talk about CIFAR10 a bit, but now you add like a consistent pattern on top of these images. Like it's not visible in the slide, I'm sorry, but for example, to airplanes, you might add like a small rain-like pattern on top of them. So you overlay each image of airplane with the same consistent pattern on top of it that neural networks can be good at picking. So as I said, they evaluate by generally testing on clean data. So this is this part. And they compare vanilla training to theirs, and they compare against different ratio of examples with the shortcut, right? So how many? What's the percentage of examples that have all images aligned with color? And for example, and they show pretty big gains. In this case, there is like plus 20%. In this case, there is plus 20%. Of course, again, it's a weird experiment in a way, right? Because you have a very big shift between training and testing. But I think it's a useful benchmark, and it emphasizes that something that, in my opinion, is wrong with deep nets, but that's another story. Then there's the second approach, which is basically just use larger data set, which I think is actually pretty smart. So maybe the first paper that really demonstrate this, or like 2 papers in parallel, was Align from Google and Learning Transferable Visual Models from OpenAI. In both papers, they collect a lot of images from the web associated with text. So for example, we have a motorcycle wheel with text, motorcycle front wheel. And in the OpenAI paper, they have 400 million images like that. And that contrasts with just 14 million images in ImageNet. Yeah, for me, it sounds weird to say it's just that, but yeah, that's where we are. And I really loved the main experiment in the paper. They compared ResNet that was trained just on ImageNet with their model that is performing inference zero-shot on ImageNet. The way you do zero-shot learning with this model is that you describe the image, right? Like it's a banana, and the model can then search for images that correspond to text. It's a banana. And here are examples of one of the classes of ImageNet, bananas. And coincidentally, ResNet and the model clip gets 76% on this data. That by itself is pretty remarkable. But then things get more interesting. If you test on sketches, then there is plus 35% of gain for the clip model. Then there is this ImageNet adversarial that has all sorts of weird bananas. So for example, there's front-facing banana, so you don't see the curvature here. There's like banana, I think, glued to the, banana on a plate, banana next to a lot of papers, a lot of sheets of paper. So in this case, ResNet gets 2% and the model gets 77%. I think that's a remarkable experiment and really illustrates the power of not training for a task. I think that's a very important concept. Yes?
And just to clarify, is this ResNet trained on standard ImageNet or on this?
Yes.
Oh, okay.
Yeah.
Does it mean that it tells us that strong augmentations is all what you need for training a model? And the second question is, do you know about some results in self-supervising domain which relates to simplicity bias and what you are telling right now?
Okay, so first question, if you think about augmentation as having more data, then yes. I mean, having more data is all you need. That's one way to phrase it. And not sure about self-supervised learning. Sorry, I'm not sure what would be here relevant. But for sure there are some papers, but I'm not very familiar.
The model-to-one clip is just a classification, or is it outputting the text, caption text?
That's classification.
Classification, yeah.
But isn't this the opposite of using simplicity bias? So like while you're giving the natural language supervision, you force the network to associate with a specific concept, something that maybe it would have learned in a different way if you didn't have that kind of supervision. So you're removing the simplicity away and only focusing on what you actually care about. So
I don't know. I don't fully understand your question. I don't think it's really about using or not simplicity bias in the sense of any network has a simplicity bias. So maybe the answer here is changing simplicity bias, but mainly actually it's all about data size. So yeah, I'm not.
So like if you show 400 million images, but without the natural language supervision, it might catch on different features. Well, if you actually say all of these are bananas, then it extrapolates more complex features that maybe if without the supervision.
No, that's a good point. I'm not sure how this relates to simplicity bias, but indeed text like adds, somehow restricts the learning task, but also adds data. There are two effects. So, but thanks for the question. I'm not sure how to answer it.
So I first thought simplicity bias means that it learns like very general, simple features. But I guess what you're saying is that it's not the case, right? It sometimes might learn simple features which are totally wrong, right? Because if it would learn very simple general features, it would generalize to the banana stuff. So it learns simple but often incorrect features, and it should learn simple but meta features.
Yeah, I think that's a good way to phrase it. Maybe I can rephrase it in the sense that if you have, here I basically talk about two ways to combat shortcut learning. And shortcut learning is this example where you learn the wrong simple stuff. So for example, when you train an ImageNet on, a ResNet on ImageNet, your model relies a lot on texture. So it will bias strongly prediction of certain classes by just there being like more high frequency features. Like for example, fur of an animal would be high frequency feature. And then if you overlay fur of an animal on bananas, it will think there are like animals. So indeed, having a large diverse models kind of cancels out the wrong simple features in this case. And I think when we think about training large language models on huge data, like I think it really, well, one way of thinking about this, and again, this is like my opinionated way of thinking about deep nets, is that it amplifies what works everywhere. And that becomes the simple stuff it learns at the beginning. So if you have, let's say, in your data set images of bananas with some sort of texture, then this will deprioritize for the model learning to use texture in classification. So there is this, if for someone it is confusing what I'm saying, there is a whole line of research where people are showing that CNNs, so convolutional neural networks, learn a lot of texture to classify. So they try to detect textures in the image, which does not always generalize to other data sets.
Okay, thank you.
Thanks for the question.
I have a question, whether the effect of the additional data, meaning the text, was explored, because in theory you could take the larger data set and label it in the same sense as image that is labeled, and then train so that we would have only the difference in the size of data, right?
Sorry, I'm not sure I understand the question.
Like taking the labels from ImageNet, because I have
right. Okay, sure. Yeah, you can turn ImageNet into dataset with text and images, but the whole thing is that these these labels are very, very diverse. So for example, Clip learned to associate images with geographical location. And that comes from the fact that some texts are like, St. Oswald's Way and shops. So that's what I was saying, that this is a lot of additional data in a way. It's not just the label, it's like all sorts of labels in the image are annotated.
But I'm asking whether the data in the text or the data in the image, like the larger amount of data in the images, could solve the problem, not necessarily the text, right? Because your image not in.
Potentially. That's the whole question of role of language in deep learning. I don't want to go into this rabbit hole, but I think there is a bit more to that than just number of data. But in this framework of thinking, yes, indeed, that's just weighting more data versus more data from another domain. Yes.
So maybe a better word for this bias would be actually shortcut bias. Because I thought about it, and I guess the real thing that might be happening here in the network is that it just learns all the very stupid, simple shortcuts in the first place. For example, if it's like, this is a human, it thinks maybe it has skin and it has hair on its head. And some of these might be simple general features like having skin in your face, but maybe hair on your head doesn't have to be like, so it might just learn stupid shortcuts in the beginning. So stupid shortcut bias might be, would that be maybe a better way to name it?
Maybe. Sure. Yeah, I mean, that's the good and the bad, right? Like the simplicity bias and there's the shortcut learning or shortcut bias. Sure. Yeah, you could say that, yeah. I think. Any other questions?
Wouldn't you say that, especially this example, actually says that multitask training could improve this shortcutting error?
Yeah, it could be. There are all sorts of ways of framing this. Yes, indeed, if you can think about this text data as just doing multitask learning, where you're predicting all sorts of labels. So I guess that's a solid way of thinking about this. Okay, thanks for questions. How much time do we have actually left?
A little bit less than half an hour, but
that's a lot actually. Okay.
Okay, so we have like 20 minutes.
Yeah, maybe let's make it 20 minutes. Yeah, cool. Okay, so as I said, this talk is very modular, so I won't give you theory. I don't know, for those of you who are very theory-oriented, sorry. But also you can catch me at the coffee break, so I will be hanging around. So what I wanted to, let's say, talk about also is how, well, we have done work on identifying simplicity bias, but also it is really a way I'm thinking about neural networks. This comes from a paper we have recently published in Nature Scientific Reports called Difference Between Human and Machine Perception in Medical Diagnosis. So that's the starting point. Group I did in postdoc had this amazing model for classifying breast cancer. It's from a paper, Deep Neural Networks Improve Radiologist Performance. So the task is that you are given mammography images. It's worth emphasizing maybe that breast cancer is one of the leading causes of death for women, unfortunately. And the task is to read this image. It's extremely large. It's just shown here as a small image, but it's really like thousands of pixels by thousands of pixels. And there are like tiny changes in this breast that are associated with cancer. And then the task is really a classification task. So you're asking whether the breast has any change that's cancerous. And if you just take radiologist, a single radiologist, his ROC AUC is 77%. A single model is 87%, and that's important. That's a convolutional neural network. Ensemble of radiologists is 89%, but then if you ensemble everything together, you get 90%. I think we are really going into the future where these type of models would be used on a routine basis. But before we do, I think we have to understand what sort of things, how they reason, right, about the images. And how models reason here is still an open question. And we approached it from the perspective of simplicity bias. So one thing that people have noticed is that deep convolutional neural networks exhibit texture bias. I did refer to that briefly during your questions. Here is a paper that illustrates that. So we have again an ImageNet, and we feed it these 3 images. We have again ResNet trained on ImageNet, and we feed it 3 images. We feed it a close-up of elephant skin, and it classifies it as elephant with high confidence. When we feed it image of a cat, it classifies it as a cat with high confidence. And when we overlay the two, the model, and that's a very broad phenomena, it classifies the image as Indian elephant and ignores the fact that there is a silhouette of a cat. For context, vision transformers trained on very large data do exhibit much less of this bias, so again, diverse data helps, right? So this model was a convolutional neural network trained on millions of mammograms with associated biopsy results, so it's actually a very expensive data set to collect. And we thought that maybe these CNNs have some form of texture bias. We weren't really specific on what exactly is happening, but we had a clue that we should look into this. So what we did is very simple. We blurred mammograms and fed them both into humans, so to speak, and into models, and looked at differences. This here plot shows how we exactly did blurring, but that's not that important. We performed Fourier transform, then we removed frequencies that are in the middle, so low frequencies, and then you get this sort of image. I mean the other way around. We remove high frequencies, which are far from the center, and you get that sort of image. But you can, of course, also just do like convolution with Gaussian kernel, and that's the same. So the experiments we ran generally were of this form, that we are comparing radiologists. So that's the interesting thing about this experiment, that we fed radiologists with blurred images. I don't know if people have done it before, probably not. And there is DeepNet on the same data, and there is DeepNet that has been fine-tuned on blurred images, so it's more adapted to them. On x-axis, we have the severity of the filtering. It's from 0 to 4 in some units. 4 is like really blurred, like you cannot see anything. And 1 is already very blurred. I think this is like 1 or close to 1. And on y-axis, I won't go into details, like there is a lot of, let's say, math and analysis in the paper, but we have a metric called class separability, where you can basically think about this for the purpose of this TOGAS ROC-AUC, like some form of classification performance. The higher, the better. So if we plot the data, we get that radiologists are much less robust to blurring than DeepNets. And actually, DeepNets are robust to blurring fully up to like around 1, which is remarkable because these images are really blurred. So this emphasizes or shows that DeepNets and humans process this image probably drastically differently. Now, maybe just a word about why blurring is important. So here is 0 and 0.5. And a fact about breast cancer, its main feature or important feature are so-called microcalcifications. These are changes that are visible as white dots in the breast. And with 0.5, it's really hard to make out them, especially some of them, right? That's very, so it was really surprising that you can blur image, because microcalcification in the scientific literature of breast cancer is such a key feature. I guess when radiologists screen for breast cancer, they are given guidelines to look for these features. So in this region of this image, we can say that blurring images in this region has no impact on the discrimination ability of the DeepNet, especially the one fine-tuned. But we also found that DeepNets not only can process blurred images, but they're also pretty good. They also look at different parts of the image than radiologists. So to do that, we ask radiologists where they look, and then we blurred the outsides of this region and the inside and compare the two. Yes, please.
Maybe this kind of answers the question I wanted to ask, but I was wondering if you did any kind of saliency maps or other explainability analysis to see whether the nets actually focus on the cues that you mentioned before.
We did that. We didn't do saliency masks. I'm not a big fan of them. I think interpretability methods are really easy to fool us. So we did something more causal, so to speak, where we removed information from the model. So this is different data. So now colors are whether you remove interior, exterior, so it's region of interest interior in blue, region of interest exterior in orange, and entire in green. And if you look at data, again, models are very robust to removing these regions. So they seem to not be looking where radiologists are looking, basically. Like that's the main thing we noticed. And I won't go into more details about the paper, but to summarize what I wanted to say and what's the, let's say, conclusion from these results, which the paper goes into much more details. We started here from thinking from first principles, what sort of deep net, what are the features that deep net likely relies or doesn't. And the key, and by focusing on the network simplicity bias, we noticed that deep convolutional neural nets process much better blurred mammograms by looking at features that humans do not. And I think we should solve for this if we want to deploy this in clinical setting. I think that's important. And this feature could be either an important biomarker, which wouldn't be that maybe surprising because we still know kind of very little how to detect these changes, or important limitation due to which we shouldn't use these models in clinical setting. And one thing that I wanted to maybe leave you with in this presentation, generally speaking, is that there is not only simplicity bias, but also it is somewhat, let's say, unsettling that we are leaving a lot to how our deep nets work, to what is learned in the early phase, and what's worse, we do not control that. So please go mentally back to the induction head. No one designed for the induction head. And I think a lot of what happened later in deep learning that culminated in things like ChatGPT is really downstream from the emergence of induction heads. So I would argue that it's very important to not only think about simplicity bias, but also try to design for it, if that's possible. And largely right now it's not, and I think that's a problem. Yeah, do you have any thoughts or questions about this section?
Isn't it kind of contradictory that DCNNs are sensitive to texture, and then you show that when you have a filter on the image, it does well?
Yeah.
Doesn't that indicate that it's not sensitive to textures?
Yeah, I wanted to say that in the beginning, but I guess that was confusing. Like we started from thinking from first principles what they should be sensitive to, and then we found the opposite. Yeah. And that was also a discovery, right? And I don't know why this happens. Like deep convolutional nets are indeed very sensitive to texture, but not in this case. There are two things that could have happened, and we haven't discriminated between them. First, maybe they are sensitive to texture, but humans are much more. That's possible. And second, maybe the data was such that it actually forced the model to unlearn this bias. And if so, it seems like a huge inefficiency in training because we use that data to unlearn a bias of the model. So either way, yeah, there is an impact on simplicity bias on this outcome.
So I wanted to ask something which I think is related to this question.
Yes.
I think these results with blurring are very interesting, and so I was wondering, because if you consider CNNs on more standard tasks, like what you would normally do, like recognizing cats and dogs and human faces, then these are more prone to some data shifts than humans, and some adversarial attacks or even not adversarial. While here you show that it is the opposite. So
yes.
Do you have some intuition, why is it the case, and is there a reason which is connected to the like the form or character of this task that we as humans are like super optimized to like recognize human faces, or like not optimized to, you know, be radiologists. So is it the reason, or like?
Yeah, thanks. I don't know. That's short answer. Like one thing that could happen here, could have happened here, is that there are strict guidelines and trainings for how radiologists should work. And in particular, these guidelines and trainings emphasize the need to detect high frequency textures, because a big biomarker of breast cancer are high frequencies in the form of these microcalcifications. Hence, maybe we are overtraining the humans, right? So we are kind of, forcing humans to use one set of features, and maybe they are, walking away from using other forms of features that are useful. Or maybe they are doing the right thing and the models are picking up on something weird. Yeah, thanks.
I was wondering over here. Basically, we observed that the neural networks pay attention to different parts of the image with respect to radiologists.
Yeah.
But are different neural networks trained, for example, with a different seed, paying attention to the same part, or is that part random?
Right. That's a good question. Like, we haven't checked that. Thanks.
Hello. Yeah. Was the model trained on radiologist annotations, or did they also have the ground truth of whether the area it actually was breast cancer, like from biopsy?
Yeah, that's a very good question. Indeed, like the key thing about this data set is that these are true biopsies, so it's very expensive to collect, and so these are true ground truth labels.
And I guess will a radiologist get this feedback loop when they are in day to day?
That's a very good question. Well, that's one thing, right? Radiologists, but also doctors are not really trained in this closed loop fashion. None of them in no hospital, basically. Like I think there are like case studies and things like that, but it's not a structured process, and I think there is a lot of room for improvement.
I was wondering if is there any sort of mass conservation property or something like that in a Gaussian blur filter that could leave the signal behind in some way, even though you don't have this exact spot, you still have the mass or something like that?
Sure, I mean, maybe, but it is detectable for deepness and not for humans. Doesn't change conclusions.
Okay, you said that you're not fan of attention and saliency maps, so do you have any ideas how we can analyze what's going on inside? Do you have any, I don't know, techniques or tools for that? Especially in medical image domain.
Sure. Yeah, next section talks briefly about this, so maybe I can mention a few thoughts about this, but also I think we won't go into the next section, so maybe as means of answering your question, but also that's to others as well. So what I wanted to talk next is kind of what's next, all of this, and in particular to your question, we are trying to solve for a problem that we train a neural network in this weird way where we just, give it data and it churns out a magic model, and then we try to interpret it. And that's probably, in my opinion, probably wrong. And I think related to a different question, we should probably train these models more on how to think, not what is the outcome. And then interpretability will probably follow. And language has a big role probably in it. So kind of that's what I wanted to say in this section. That's also partially answer to your question. But a short answer, I think, kind of based on techniques that we have right now, is that we are in a pickle in a way. Like it's very difficult right now to interpret neural networks. Language models, for example, allow a lot of interpretability through things like chain of thought, but this can be really misleading as well, because sometimes they don't show correctly the reasoning, sometimes they withhold facts. So it's work in progress. But I think we need a new way of doing deep learning to really solve for interpretability, and doing things like saliency masks is probably more of a distraction, I think. but it has its room. Like I don't want to have an umbrella opinion. It's kind of broadly speaking.
Okay, so I just wanted to ask in a very precise case when, for example, you have some medical image with, I don't know, on the cellular level from biopsy. And for example, do you think it's at all worth it to, for example, do some statistics on comparing which object relates to each other with saliency maps, or do you think this is just a waste of time for?
I think. So how we, for example, at molecule.one, to kind of speak closer to home, try to think about this is you can use saliency masks and things like that for generating a hypothesis about what your neural network thinks, but not to know what your neural network thinks. So you generate a hypothesis. Let's say you see consistently that saliency mask looks at this part of an image. Then you go and make an experiment in the real world to see if that's the case. And what the real world might mean here is, for example, asking humans for annotation of modified images and comparing that with neural networks. So that's called contrast sets, or related to contrast sets in natural language processing. So basically treat the saliency masks as hypothesis generation tool, not as a tool that tells you what's going on in the network. And then based on the tasks you are in, you can make all sorts of different causal-like interventions to understand the model. Thanks. Yes, please. I knew it's coming, but I'm not sure we have a lot of time. Sure. So maybe by analogy, I hope this will be a productive way. We still, I think, have 5 minutes in the 1.5 hour slot. So anyhow, there's a lot of stuff, but one way of thinking about what's going on is, I think there is an analogy between current deep learning, which I call deep learning 2.0, which again, you might have questions what the heck it is, but it's current, what we do currently in deep learning. So I think you can draw here an analogy to evolution. So the prevailing way of thinking about evolution, or how it happened, is that there was this primordial soup, right? And in it, you had precursors, or all sorts of compounds that are currently part of our body. For example, there were lipids that, according to one theory, formed the outer cell. And then from that, you get TikTok, and there's like a process in between, right? That's very unclear. And I think it's similar with deepness, that we have models that we tell ourselves stories about how they do the tasks we think they do. But actually, the process is very nonlinear and hard to understand, and hence also it's hard to engineer for. So I think the next phase of deep learning is really about solving for this, in the sense of, instead of having by accident capabilities, I think we are moving towards a future where we have capabilities that are engineered, and they can be engineered in particular by supervising the model on the thinking process. So that's the gist of what I wanted to say. Any other questions? Maybe let's go back, so that's not confusing. Okay, please.
Do you think that when you supervise the model on the thinking part, you essentially cap the capabilities to human level?
Yeah, that's a great question. One way of thinking about this, and I'm not sure if this is in literature, so it's probably more of my opinion, is that you can also supervise the model on thinking, not by human feedback, but by making experiments with the real world. So for example, in the paper, Let's Verify Step by Step by OpenAI, they perform the supervision of the thinking in the context of mathematics. So there you can verify the thinking more, let's say, in an unbiased way, either using an automated solver, or really humans can say what was the correct step in mathematical reasoning.
Thank you. Yeah,
that's a good question. Thank you. Okay. I think we can finish at this point, so let me just summarize everything and skip again through the section. But happy to talk about this in the coffee break, during the coffee break. So what I wanted to say, and 2 of these boxes were not what I said, so because we skipped them, and I think that's fine. The deep nets learn first simple patterns. For example, transformers learn induction heads that can be early on, that can be causally linked to a lot of in-context learning capabilities. I said that unfortunately deep and biological nets also learn first shortcuts, and there was an example of Hans. I also mentioned that shortcut learning can be reduced or alleviated by leveraging the simplicity bias itself, and also, maybe more importantly, by just increasing the dataset size you have and its diversity. And then I mentioned how thinking about simplicity bias enabled us to unearth, let's say, uncover surprising classification rules of a radiologist level deep CNN. That's quite important, that it really performs well at this task. And I mentioned very briefly that we should move towards engineering the training process. And I haven't really mentioned that, but I think that language is a promising tool for that. So language understanding models. But really the main message of the talk is that to understand deep learning, you have to understand simplicity bias in your system. And the simplicity bias is connected to all sorts of questions or phenomena that we see in deep networks that are quite widely spread. So from things like why can we train nets on such noisy datasets such as internet, to how does deep CNN beat radiologists, to why does transformers sometimes fail to robustly generalize. All sorts of these things have really their roots in the so-called childhood of the model, so the first phases of training where it acquires a lot of these basic capabilities, then it builds upon them, as I was trying to describe. So thank you very much for listening. Yeah, any other questions, I think, or do you have time for last ones?
Okay, I will take the last one. So I like the, I was waiting for this question from the very beginning. So I like the comparison with the title to evolution.
Yeah.
But also, like, as you pointed out with the example of the horse, like, evolution is like strictly looking for the shortcuts, right? Like 99% of the species are already extinct. Is it like something normal, and we shouldn't, in that sense, be worried about that? That's, you know, like, firstly we build CIFAR 10, and then we have like this massive data set that we cannot process, and it's something normal. And like, I'm not saying that's a problem, but like, it's something that we cannot avoid anymore.
Yeah, it's possible. Evolution is highly nonlinear, in particular. So yes, it's possible, but still, it's the way to think about deep nets, even if this is just how we have to live with it. But I personally think that there is a lot of room for engineering the thing. And I think that also, I mean, that's another argument, by the analogy to other domains. So, you know, initially, for example, when we built bridges, we didn't really understand them. And then, you know, we started to have all sorts of things like finite element method, you know, understanding of strains and tensions and things like that. So I think there is room for engineering deep learning, or at least supervising it on how it thinks. And I think that's critical for emergence of some of the use cases that we want, such as you know using them widely in medicine and things like that. But really, I don't know. Maybe we'll just continue like that. We'll just scale the models and do something on top of them, and it will work. And it is possible as well. Like, I'm not really trying to pick a camp here. I think there is a range of possibilities, and we should acknowledge all of them.
Okay, many thanks again, and we have around 25 minutes for the coffee break.
Oh, thank you.